Okay, so we had a little technical trouble, but what I was saying was, this is going to be in 3 units, I'm sorry, but at least there is a review. I probably should go into school and do these on integrity. But anyway, what I was saying is, if you put this protecting group on, you can take N-butyl lithium. This will attack here. This will pick up the lithium. Remember, there's stereochemistry in this problem. Just to kind of outline what's going on. I'm really worried that you guys are not going to see acidic protons. It makes me nervous. Okay, I would do this, then I would add my acid. Okay, this is going to enable this to pick up a proton. Right? So then you get that, but then you have to take the protecting group off, and it has to come off under different conditions. And the conditions for this are kind of peculiar in that you use ammonium fluoride. It's amazing because there's all kinds of protecting groups, and as I told you, protecting groups are not as hip as they used to be, but you should see some, and people do still use them in spite of what they say. So you get this. Now notice, this already has chirality, so you get this plus its mirror image. Not its mirror image, right? Plus its diastereomer. Because this already had a pre-existing asymmetric carbon. Don't forget about that concept. Okay, we've covered a lot of ground. There's one last thing I want to do because it's really hard. Okay? I have to think of a clever way to present this to you. I did it one way in class. I did this parallel thing. So the thing I want to tell you is that anything that has, so this is reduction. Okay, and you do have to know how to reduce a number of carboxylic acid derivatives. So the reduction of a carboxylic acid is the same as the reduction of an amide. Okay? And this is the last thing I'm going to talk about in this review. Okay, it's the same thing. And the reason I think this is useful is it pretty much covers all reduction. All right, and I'm going to do this, I'm not going to write out all the mechanisms. I'm just going to talk a little bit about what's going on here when I add lithium aluminum hydride. Okay? Lithium aluminum hydride is a hydride reagent. It produces hydride. You've learned 3 things hydride does. Hydride pulls protons off first, attacks carbonyl second. Okay? That's kind of what it does. And in the second attack, it can knock a leaving group out. And then in a third attack, will reduce a carbonyl. Okay, so in these reductions, this shows the whole gambit of what a hydride does. And why does it do this? Because it's a ridiculously strong base. And by the way, Grignards do something very similar. You'll see me do an ester tomorrow in class. So they remove protons first that are acidic. Why? Because they are a ridiculously strong base. Hydride, conjugate base of H2. Okay, 2, they'll knock out a leaving group. Three, another thing they can do is just reduce a pi bond. That's what you're used to. And I think what I have to say to you is you started here, we started here and you already knew this. Then we added this in. Then we added that in. We went in that direction. So all parts of this you've learned, and it's like putting a concert together. You have to put the whole symphony together. Okay. So the classic example is this one. Maybe I'll do this one because this is the harder one. But what happens is what happens here, is the hydride comes in and just rips that H off. And by the way, it does the same thing over here. It rips that H off. Okay, upon ripping the H off, you end up with a resonance stabilized anion of an amide. And you might say to yourself, why? Why does that H come off? Because it's allylic, right? There's a resonance form here. Now what's important here, and this is kind of interesting, it doesn't always work out this way, but what's nice here is that this is the form that actually undergoes the chemistry. Okay, in other words, the form that you would have evaluated and said, this is the more important form, that undergoes the chemistry. Now this does the same thing. I'm not going to write out all the steps, but it does the same thing, and it ends up like this. All right? They both bond up to aluminum. Okay, so this gets bonded up to aluminum. And as I said, you can be very, very liberal about what's hooked onto that aluminum. It's either hydride or some kind of like alkoxide. Same thing happens here. This gets hooked to aluminum. All right? Step 1, we remove the hydrogen. We drew the most stable resonance form, and we hooked the aluminum up. Now we're ready for step 2, knock out a leaving group. The next hydride comes in. Practice this a couple of times. What I'm focusing on here are processes that people have trouble with. But anyway, what happens is this goes in. I'm really grossly over-abbreviating because of time. And that comes out. Those are not one step. I don't want to see that. I don't want to see one continuous step unless you're just thinking through it to get an answer. If it's asked for a mechanism, you would go in, you'd go up, you'd stop. You'd bring it down, you'd bring it out. So this is sort of like 1, 1, 2, 2. I'm cheating a little bit here, okay? Same thing happens here. The hydride from the aluminum, from another aluminum, or the same one, it doesn't matter, comes in, this goes up, this goes down, this comes off. Okay. So then what's the last step for both of them? The last step is reduce the pi bond, the resulting pi bond. So this is the kick out. Okay, and I'm going to have to stop here because otherwise we could spend like 6 hours doing review. We repeat the entire course. This is like my mini course. So with a carboxylic acid, all right, and again, think through what I just did. With the carboxylic acid, what happened was the hydrogen came off first because of the base. Then the O linked up to the aluminum, and then another hydride came in and knocked that whole thing out as a leaving group. So you're left with an aldehyde, a measly little aldehyde. So it should make sense to you that LAH, if there's enough of it, should reduce this because you know this mechanism into a primary alcohol. Okay, so this is a way to make a primary alcohol. Now on the other hand, the amide comes out like this. It's double bonded to N, and it might have an R group hooked there. What I want you to realize is these are just like carbonyls. This is delta plus. Let's say there's an H here. This is delta plus. This is delta minus. So when you have lithium aluminum hydride, it's a stick reaction, okay? This is going to go in. This is going to come up like that, period. All right, what's going to happen? So I don't know, I may have lost a hydrogen there. This is negative. This is going to hook to the aluminum, and then you're going to have to wash it off with H3O+. But the outcome of this will be an amine. And if you want to see some of this, I have some worksheets that I still have to write out from Friday. I have to give you your answer key to your worksheets, to your quizzes, all this stuff. I did cut a few steps there just because of time. It takes a really long time to load these up onto YouTube. Okay, so expect a couple of these over the course of the day. And then again, go over any worksheets that I handed out. The big thing to do this week, really, I've just been telling people, get your notes in order. Figure out what's wrong in your notes. Supplement your notes from your book or from other people or from coming in and asking questions. Put Post-its every place you have a problem. Go through those flashcards. You have a week. You should be able to do this. Okay? All right, I'll see you in class. Bye.